Okay. So in the last class, we have seen different things, right? Like we have seen what is the voltage buildup in a uh, shunt generator. Okay. We have seen what is the voltage buildup in the shunt generator, as well as what are the critical field, what is the critical field resistance of the shunt generator. All these things we have seen, right? We have seen in various cases how the voltage buildup is being done, and all those things we have seen. All right. So um, these are the three different types of generators we have, right? Series, shunt, as well as compound generators. So in this series shunt and compound generators, how the voltage buildup is being done for the generator we have seen, right? Apart from that, we have seen what is the critical field resistance for a shunt generator. What is meant by critical field resistance, and how is it quite important? All those things also we have seen in case of a shunt generator. So what we'll be doing is that critical field resistance is the minimum field circuit resistance for which the shunt generator would just excite. That is where the total voltage buildup is successful. That the resistance at which the voltage buildup is successful is called as the critical field circuit resistance or critical field resistance. So this is for a shunt generator. Okay, now we are going to see a similar thing for a series generator. Okay, so here is saying that figure 3.6 shows us the voltage buildup in a series generator. So here 3.5 is for shunt generator, so we are seeing 3.6 for series generator. Here also we have an OCC which we have now please stop with the emojis, okay? And I can't stress it, but it's really annoying. So please stop using those emojis in my class. Okay? So this curve which we are seeing, this curve is called as the open circuit characteristics or the magnetization characteristics. Now he is taking the critical field resistance circuits, critical field resistance lines, that is R1 is one of the field resistance line, R2 is second line, RC is one, and RD is one, that is ABCD are the field lines, and using these field lines you can see how these are being added and all those things, right? So what we are going to by this what we'll understand is the resistance at which the field resistance circuit becomes a tangent to the OCC, there we call it as the, that resistance is called as the critical field resistance. In this case RC, that is the C line, is becoming a tangent to the OCC, right? When the resistance is RC, then the C line, we are drawing the C line, and while drawing the C line, you're seeing that these are not, that is becoming a tangent to the OCC, right? So when it becomes a tangent to the OCC, then that resistance, that field resistance is called as the critical field resistance. So in this case, that is in 3.6, figure 3.6, you can see that ABCD are the field resistance lines, right? So in that ABCD, C is becoming the tangent to the OCC. C is becoming tangent to the OCC. So C, the resistance C, the resistance field resistance for the C line will become the critical field resistance for this particular machine. So as you can see, that is what is going to tell us here. Here R1 and R2 etc. represent the total circuit resistance, load resistance, and the field winding resistance. The total circuit resistance is R1 when series generator will build up an voltage OL. Okay, the just by understanding this you can see here. So if the R1 is the field resistance, sorry, R1 is the circuit resistance, then the voltage buildup, the maximum voltage buildup that can be happened is OL. That's what he's saying. Okay. Next, the line OC is the tangent to OCC and represents the critical field resistance RC for a series generator. That's what we are seeing. If the total resistance of the circuit is more than RC, say line OD, then the generator will fail to build up voltage. So for the voltage build up to happen, for the machine to excite, the minimum field resistance is called as the critical field resistance. That that critical field resistance, or the critical resistance in this case of this series generator, is represented by the line OC, because OC is becoming tangent to the OCC curve, that is the magnetization curve. When it becomes a tangent to the magnetization curve, it is showing us the minimum resistance that is to be there in the circuit for the voltage buildup to happen. So that is how we are going to analyze. Okay, so first thing what we are going to do is, uh, this I'm talking in the perspective of understanding all the things like lab and all. Okay, so if you're going for the lab, then what we are going to do is we are going to perform a, what do you say, experiment in which we will be drawing the OCC, that is the magnetization curve. And after drawing the magnetization curve, what we are going to do is we are going to find out the tangent, at which point the tangent is drawn. Okay, from this tangent should be always present from origin, and it should meet the curve. Tangent means it should meet the curve only at one point, right? Now in this case, if you see, OC line is only touching the curve at one point, right? Only at this point it is touching. So this will be your critical field, or the critical resistance, right? So we need to, when we go for the experiment part of this, what we are going to do is we are going to draw an OCC. Along with drawing an OCC, we'll find out at which field resistance, or at which resistance does this particular machine get its critical field. We need to find out the critical field value. So what we'll be doing is we'll be drawing a tangent to the OCC, which is going through the O, that is the origin, which is going through the origin. And then we'll find out the point at which the tangent cuts the OCC, or where it touches the OCC, and then from there we'll find out the critical field, the resistance that is required for the voltage buildup. Okay. So if the resistance is more than this critical field resistance, then what happens means the voltage buildup will not happen. If the field resistance or the circuit resistance in case of series generator is more than the critical resistance or the critical field resistance, then the voltage buildup will not happen. The machine will not start itself. So we need to make sure that the machine has certain value of resistance which should not be, higher than the critical field resistance, and it should not be less than the critical field resistance. Okay, it should be exactly the critical field resistance, such that we can have the voltage build up in a successful manner. Okay. Note that the figure 3.6 is similar to figure 3.5 with the following differences. Okay, here is giving us a comparison between a shunt generator as well as a series generator. So we have both the figures, that is 3.5 as well as 3.6 in parallel here. You can see that. Now he's saying that they are quite similar but with a slight differences. Let us see what are those differences. In figure 3.5, R1, R2, etc. represent the total field circuit resistance. However, R1, R2, etc. in 3.6 represent the total circuit resistance. So, he's saying that in case of 3.5, that is in case of a shunt generator, that R1, R2, RC, whatever we are seeing are the field resistance, total field resistance. Whereas in case of a series generator, you will not have it separately, you will be having the total circuit resistance. That is the difference between these two figures. In figure 3.5, field current alone is represented along x-axis. However, in 3.6, load current is represented along y-axis. I don't think it's y-axis, it is x-axis, right? Yeah, x-axis. X-axis. Note that in series generator, field current is equals to load current IL. So here if you see, the x-axis of this shunt generator is represented by the field current of that particular shunt generator, whereas in case of the series generator we are having the load current. Why are we having the load current? Means in series generator whatever the current flows through the field windings of that particular machine will also be the same current that is flown through the armature as well as the same current that is flown through the load. So whatever the load current we are having, the same amount of current will be flowing through the windings, field windings. That is why we have x-axis as IL rather than IF as in case of shunt generator. Okay, that is another major difference which we need to understand. Okay, so basic differences are in case of the shunt generator, the field resistance which we are taking is the total field resistance. So only the field resistance is being taken and that plays an important role in the voltage buildup for the shunt generator. Whereas for the series generator, total circuit resistance is being considered, and the total circuit resistance includes both the armature resistance as well as the series field resistance. Okay, so that's the first major difference when we are comparing these two, and the second major difference is the currents. In case of the shunt generator, the amount of current that is being flown that is being considered is the field current, whereas in case of the series generator, the amount of current that is being considered is the load generator, as the load generator is the same amount of current that is being flown through armature as well as field as well as load. Okay, those are the major differences which we need to understand. Cool. Next is till now we have seen the characteristics of different generators, right? So we are going for the next characteristics, that is the characteristics of the series generator. Figure 3.71 shows the connections for the series wound generator. Since there is only one current that which flows through the whole machine, the load current is the same as the exciting current. This we know, right? So this is the circuit for the series generator. We know there is a armature and there is a winding and then there is a load directly connected, right? Now, first thing is we need to, we are seeing the different characteristics. So we'll be having mainly three different characteristics, right? So the first one is the open circuit characteristics or the magnetization characteristics or OCC in short. And again we have internal characteristics as well as the external characteristics of a machine. Alright. So first thing is OCC. Here curve 1 shows the open circuit characteristics of the series generator. It can be obtained experimentally by disconnecting the field winding of the machine and exciting it from a separate DC source as discussed. So here we are going to see first thing on the right hand side you have the different characteristics of the machine. So you are seeing OCC, fine. OCC is represented by the first curve. So we are seeing the OCC. Next is internal characteristics, and the next third one is the external characteristics. So let's see what is internal characteristics. Curve 2 shows the total or internal characteristics of a series generator. It gives the relation between the generated EMF E on the load and armature current. Due to the armature reaction, the flux in the machine will be less than the flux at no load. So you people need to understand these slight differences. When there is no load on the machine, then the machine will only be supplying the losses, right? This we know. So under no load condition, you will have maximum amount of voltage that is being generated. That is E naught. E naught is nothing but the amount of voltage that is being generated in case of no load condition. There, this E naught value will be very high. Okay. After that, on load means we are having some kind of load that is being put onto the machine. Okay, when we have some kind of load that is being put onto the machine, then what happens is the amount of voltage that is being built up will be slightly less than the no load voltage. Okay, the amount of voltage that is being built up will be slightly less than the no load voltage, And again, you need to understand, another point you need to understand is the generated voltage will not entirely be reflected onto the terminal voltage, right? The generated voltage is the voltage that is around the armature. So you're going to know what is the amount of voltage around the armature, how much generation of voltage is being done. And apart from that, you have these series windings as well as loads and everything, right? So there will be a voltage drop, there will be a voltage drop or the voltage loss, and after that, after the voltage loss, the amount of remaining voltage will be reflected along the load. So the no load voltage will be highest. After that, when there is a load, you will have the EMF that is being generated, and after that you will be having the terminal voltage. So E naught will be greater than E, and E will be again greater than voltage, that is V. Okay, so you have three types of voltages, that is the no load generated voltage, and load generated voltage, and terminal voltage. So E naught will be greater than E, E will be greater than V. Cool. So due to the armature reaction, the flux in the machine will be less than the flux at no load. You know what is meant by armature reaction, right? It is the reaction of armature flux and field flux, right? So you know this. Hence, the EMF E generated under load conditions will be less than the EMF E naught generated under no load conditions. That is what we have seen. Consequently, internal characteristics lies between OCC curve. The difference between them represents the effect of the armature reaction. So here you can see. So this OCC will be the first curve which we are drawing, and then OCC is drawn under no load conditions, right? So after that, under load conditions, if you see, you will get the internal characteristics which will be slightly less than the no load characteristics, that is the OCC. And after that, we have the drop which we see between the first curve and the second curve is due to the armature reaction. So we call it as the armature reaction drop. Okay. Next is external characteristics. Curve 3 shows us the external characteristics of the series generator. It gives us a relation between the terminal voltage and the load current IL. So as we have been discussing this from the past discussions, and it is being repeatedly said that the external characteristics is the characteristics that is being drawn to the load current as well as the terminal voltage. Okay. So here we know that this terminal voltage is given by E is equals to, V is equals to E minus IA into RA plus RSC, right? This we know. This is a relationship for the series generator, right? Therefore, external characteristic curve will lie below the internal characteristic curve by an amount equal to the ohmic drop, that is IA into RA plus RSC in the machine as shown in the figure 3.72. So here you can see the external characteristics again. This will be slightly below the internal characteristics, and the difference between these two, that is the curve 2 and curve 3, that is the internal characteristics and the external characteristics, is given by the drop, that is IA into RA plus RSC drop. Okay. Okay. The internal and external characteristics of a DC series generator can be plotted from one another as shown in the figure 3.8. He is saying that by just knowing one of them, either the internal characteristics or the external characteristics, the other can be drawn. So how is that? Let us see. Suppose we are given the internal characteristics of the generator. Let the line OC represent the resistance of the whole machine, that is RA plus RSE. So he is giving us the internal characteristics, and the line OC represents the total resistance RA plus RSE. He is saying that. Then what happens? Let us see. If the load current is OB, drop in the machine is AB. Is saying that OB is the load resistance, and again AB is the drop in the machine. AB is the drop in the machine. Now AB is equals to ohmic drop in the machine, that is equals to OB into RA plus RSC. So OB is the load current. He's saying that OB is the load current. So if you just multiply the load current into the ohmic drop, sorry, ohm resistance, that is RA plus RSC, you will get the total ohmic drop AB. Okay. Now rise a perpendicular from the point B and mark a point B, small b, on this line such that small ab is equals to capital AB. He's saying that just by replicating these two, AB, capital A, capital B, is just asking us to mark these points, these 2 points, and then that he is asking us to replicate this here. So you get a point B where small b and capital B, the distance between small b and capital B is equal. Then point B will lie on the external characteristics of the generator. So he is saying that then the point B will be lying on the external characteristics of the generator. Following the similar procedure, the other points of the external characteristic can be located. It is easy to see that we can also plot internal characteristic from the external characteristic. So he is just replicating what the loss is there. He is just finding out the loss and then trying to plot the points from using the internal characteristics. He is assuming that we have the internal characteristics, right? So if you are assuming that we have the internal characteristics, if you know what is the drop from the internal to external, then you can draw the external characteristics. So just by knowing this, knowing one of them, either one of them, if you have the internal characteristics, then you can draw the external characteristics, and vice versa. That is, if you have the external characteristics, then you can draw the internal characteristics. Okay. So the next topic which we are going to see is characteristics of a shunt generator. Similar to the one for the series generator, we are going to see one for the shunt generator. Here the figure 3.91 shows the connections of the shunt wound generator. The armature current IA splits up into two parts, a small fraction ISH flowing through the shunt field winding, while the major part IL goes to the external load. So it's giving us how the connections are. Here you can see on your left hand side, you can see the armature as well as the shunt field winding and how they are being connected to each other, and we have a load. Now if you can just look at this diagram, here you can see that the armature current is being split into two parts, that is, one part is the load current and the other part is the shunt field current. Okay. Now, let's see what he's going to say about the different characteristics of this shunt generator. As you know, the first one is the OCC, or open circuit characteristics, or magnetization characteristics. The OCC of the shunt generator is similar in shape to that of a series generator as shown in the figure 3.92. Okay, so we have seen already what is the OCC for the series generator. Now we are going to see what is the OCC for the shunt generator. Here you can see he has plotted the OCC in dotted lines, is representing it is as OCC. Okay. Now the line OA represents the shunt field circuit resistance. When this generator is run at normal speed, it will build up a voltage OM. OA represents the shunt field resistance line. Just the shunt field resistance line. I am again repeating, it is not the critical field resistance, it is the shunt field resistance line. A general resistance line for the machine. If you know what is the resistance of the shunt field resistance of the machine, you can just plot this line OA. Okay, and if the point at which this OA meets OCC will give us the maximum voltage that can be built up in the machine. So if you see in this case, it is OM, because yeah, because the machine OCC is being cut by the shunt field resistance line OA. and that point, if you just look at the reference voltage of that point, it is nothing but OM. Sorry. At no load, the terminal voltage of the generator will be constant, that's equals to OM, represented by the horizontal dotted line MC. So he's saying that if you don't have any load, then the terminal voltage will be constant, and that is represented by the line MC. Now we are going to see the internal characteristics. When the load is when the generator is loaded, flux per pole is reduced due to the armature reaction. This we know, right? Therefore, E generated on load is less than the EMF generated at no load. So here you can see we have this OCC, and then we are having this internal characteristics, and this difference between this OCC and the internal characteristics will give us the armature reaction drop. We know what is armature reaction. Armature reaction is nothing but the interaction between the armature flux as well as the field flux. So if you just know what is that, then we can say that the field OCC from the drop between the OCC and the internal characteristics is nothing but the armature reaction drop. Here you can see how it is being represented. That is from the point C to E. If you can see, that is the difference. That is the armature reaction drop. Okay. Yeah. As a result, the internal characteristics drop slightly as shown in the figure. Okay, we have seen that already. Next, external characteristics. Curve 2 shows us the external characteristics of a shunt generator. It gives us the relation between the terminal voltage V and the load current IL. This we know, right? In the similar case, here we are seeing V is equals to E minus IARA, this we know, and again IA is again divided into IL plus ISH. So E is equals to V is equals to E minus IL plus ISH into RA. Okay. Therefore, external characteristic curve will lie below the internal characteristic curve by an amount equal to drop in the armature circuit. Here you can see yeah, here you can see there is a slight difference between this internal characteristics and the external characteristics. The external characteristics are further below down from the internal characteristics. So this drop is called as the IARA drop, or IL plus ISH into RA. This is nothing but the drop due to the different parameters, that is due to the different resistances present. Okay. Now, we have seen all the three types of curves for this particular shunt generator. Okay, so in this class, we have seen the different characteristics for the series generator as well as the shunt generator, along with the critical resistance for a series generator. Okay, so